As you know, we have been conducting these online talks since last October, almost every Sunday, on variety of topics uh, in a wide range, starting from quarks all the way up to cosmology, with a view to inform our members and students about the developments in different areas, apart from their regular or special areas. That is one of our objectives, and we have been doing that. And a lot of cooperation we have received from so many resource persons. And we have also conducted these talks in the Kannada, the local language, with a view to encourage the usage of Kannada in higher education. Of course, there are difficulties, there are problems, questions, but still we have to make an attempt. What for? In the interest of students. I know many of the students and even many teachers, I would say, find it very difficult to communicate comfortably in English. Only very small fraction would be very happy. So we have to make an attempt to introduce Kannada or the regional languages into science education, higher education. And this has been one of the recommendations of NEP also. They are doing something about it. And in the interest of efficient communication, that is the idea. We have to gradually do that. It may take some time. Okay. So in that connection, we are arranging talks by various people from colleges, universities, and research institutes. And today we have a very distinguished radio astronomer with us, Professor K.S. Dwarakanath from Raman Research Institute. He is going to talk about the radio universe. That is, how the universe would look if we had radio. Our eyes were sensitive to radio waves. So they are not sensitive. They are sensitive to only optical band of light. But before I request him to speak, then he will speak for, let's say, 15 minutes, followed by a question answer session. I'll just give you a brief introduction to his career. Professor K.S. Dwarakanath has worked in the area of observational astronomy, mostly radio astronomy, using radio telescopes from all over the world to address a number of problems in astrophysics. His research career, spanning 4 decades, was mostly at the Raman Research Institute, with some years working at the National Radio Astronomy Observatory in USA. During his early career at RRI, he was involved in commissioning the Gauri Bindu radio telescope and carried out an all-size survey at a low frequency of 35 megahertz to image the radio emission from the Milky Way. Subsequently, he worked with the Very Large Array Radio Telescope in the United States, Giant Meter Radio Telescope in India, and the Murchison Whitefield Array Radio Telescope in Australia to address a number of astrophysical problems. He has worked in the area of interstellar medium, interacting galaxies, gas content, star formation rates of nearby and high redshift galaxies, diffuse radio emission in galaxy clusters, an epoch of reionization in the early universe. He has taught several courses to PhD students in astronomy and the joint astronomy program of the ISC and has guided many PhD and visiting students. He has given many seminars and colloquia in national and international forums and has also given talks in summer schools and public outreach forums. He has authored more than 100 research papers. He is a member of the Astronomical Society of India and of the International Astronomical Union. He was a member of the Murchison Whitefield Array Board in Australia and of the Square Kilometer Array Consortium of India. He is a regular practitioner of yoga and goes swimming and trekking whenever there is an opportunity. So with this, I request Professor Dwarakanath to present his talk. Over to Professor Dwarakanath.
Thank you. Thank you for the introduction, Dr. Kagali, and also thank you for giving me an opportunity to speak in this forum. Can everybody see the slide I'm showing?
Yeah, we can see.
Okay, good. So what I'm going to do in the next 1 hour or so is to give you a glimpse of the radio universe, and as I have expanded it in sentence below the title that, sorry, is that for me?
No. Some disturbance. No, please go ahead. Yeah. Some people talking. Unfortunately.
What I'm going to
sorry, this is not disturbance, Dwarka. You have not gone to the slideshow mode. Therefore, it is not taking the full screen. Can you kindly switch on the slideshow, please?
I can do that.
Thank you.
Yeah, that's good.
Yeah.
So what I'm going to tell you is about how the sky would look like if our eyes were sensitive to radio waves. Many of you would have looked at the night sky. Well, certainly not in Bangalore, but maybe outside of the city and in darker areas. You would have seen millions of stars and, of course, planets. And if you were lucky, you would also have seen the Milky Way patch in the sky. And if you looked carefully, you would have seen dark patches between the stars. Now, even if you used a powerful optical telescope, you will still see the dark regions between the stars. Now, this doesn't mean that there is nothing happening there or there is no action. It is just that those regions of the sky are not emitting in the visible wavelength of the light.
Use your microphone. You are not speaking, please.
Yeah, so these regions between the stars, which appear dark, are not emitting in the visible region of the electromagnetic spectrum. So what I'm going to take you through is
Sudha, please. These people, they are. Please don't interrupt. Mute your microphones, please. I don't have control.
yes.
Mute them.
Can I go ahead?
Please go on.
Yeah. So what I'm going to now take you through is a glimpse of what is happening in those regions where we don't see the visible region of the electromagnetic spectrum. Now this is a
Who is this person? Prakash, mute your microphone. Prakash, mute your microphone. Prakash, please mute your microphone. Please, we are having a disturbance. We're getting disturbance here. Okay, please go ahead.
okay. So,
sir, actually, admin can mute all, sir. The host can mute all. Also, you should disable annotation for others so that they may not scribble on the screen. Okay? Thank you.
Yeah. Sudha, please do that. She's admin. Okay, Professor.
Okay, shall I go ahead?
Yeah, please.
Okay. So this is what I'm trying to convey from this slide is the vast range of the electromagnetic spectrum in which the universe is radiating. As you can see on the slide from the radio to gamma rays, there is 10 to the 15 orders of wavelength that's indicated in meters there. And the visible occupies only a very small region of the electromagnetic spectrum. And of course, we have sources radiating in many regions of the electromagnetic spectrum. In fact, some sources are visible only in radio or only in X-rays or only in gamma rays. And they are not visible in the visible region of the electromagnetic spectrum. So, if we really want to understand the universe in a comprehensive way, then we need to look at the universe at all regions of the electromagnetic spectrum. So today what I'm going to focus on is what is it that the radio region of the electromagnetic spectrum tells us view which we don't see it in optical. Now the radio region for purposes of today's talk, I'm assuming it ranges from 10 megahertz to about 1 terahertz frequency. A terahertz is 10 to the 12 hertz. And in terms of wavelength, it means 30 meters to about 0.3 millimeters of wavelength. What I'm going to do to convey to you, to take you through a journey in the radio universe, is to give you 5 examples, starting from the nearby planet Jupiter, which everybody is familiar with. We will look at a nearby galaxy, Andromeda. Once again, I think many of you might have seen the optical picture of this galaxy. We will look at a pair of interacting galaxies and find out what is it that the radio can tell us that optical observations cannot tell us. We will look at a nearby radio galaxy called Cygnus A. It's one of the most powerful radio sources in the sky. And then we look at the signature of Big Bang, which in fact can be seen only in radio wavelengths, and in fact optical observations won't tell you about the signature of the Big Bang. So let's look at these examples one by one. Now, what you see on the left panel here is an HST image of Jupiter. The disk of Jupiter, as you know, it is seen in reflected light, the light from the sun reflected off this disk of Jupiter. What you see in the North Pole is what is called as an auroral emission. What is happening here is the energetic electrons and protons from the solar wind collide with upper atmosphere atoms, molecules and ions, and the excitation and de-excitation of those species gives you the spectral lines, and this is glowing in visible and ultraviolet region of the spectrum. This is very similar to what we see on the Earth, also known as aurora borealis and aurora australis, depending on whether you see these lights in the northern or the southern latitudes. So Jupiter is, as you know, is about 5 astronomical units from the Sun, where 1 astronomical unit is the distance between the Sun and the Earth. And it has got many moons. The closest is called Io, which was discovered by Galileo in 1610. So the question now is, if we look at Jupiter in radio, what do we see? Do we see just what we see in the optical, or do we see something different? Now, Jupiter has been imaged extremely well with this Australia Telescope Compact Array, which is called the ATCA. This is an array of 6 telescopes. In fact, you can see all the 6 telescopes in the picture. Each of them have a 22-meter diameter dish. It's about 500 kilometers to the northwest of Sydney. It works in the frequency range of 1.4 to about 8.6 gigahertz. Gigahertz is 10 to the 9, 1 gigahertz is 10 to the 9 hertz. And this is done pioneering work in detecting atomic hydrogen gas in the galaxy, and also some aspects of cosmic microwave background radiation. Now, an image of the Jupiter head with the ATCA at 22 centimeters on 1.4 gigahertz is shown here. It's a color picture, and people routinely use color to indicate the intensity of radio emission when we make radio images. So, for example, the red is the brightest emission in this image, and then it becomes green and blue as the intensity decreases. So you can see that the radio emission from the Jupiter looks nothing like the optical picture that we saw from the HST. It looks like a tadpole, which is very funny. And now if you ask where is it with respect to the disk of Jupiter, that's where it is. the disk of Jupiter, this is true to scale. The disk of Jupiter is actually between those two bright emission that you see. So, so the radio emission is actually coming beyond the disk. And if you look at, this is, for example, is an image, the radio image is at 1.4 gigahertz. It has also been observed at lower frequencies, like, for example, 600 megahertz or 300 megahertz. And in fact, the intensity of the radio emission that you see in the two spots, for example, it actually increases in brightness as you come to lower frequencies. This is what we call as non-thermal emission, the non-thermal radio emission. I will indicate to you in the next slide what it means. The figure here, for example, the figure at the top, what is plotted along the y-axis is the intensity of radiation, and what is plotted along the x-axis is the frequency. Now, we're all familiar with the thermal radiation. Let's say, think of a black body emission, which is just due to temperature. Now, the thermal radiation, one of the characteristics of thermal radiation is that its intensity decreases as you come to lower frequencies. If you look at, for example, black body radiation, it is unpolarized, and the intensity decreases towards lower frequencies, as is seen in this plot here. And at low frequencies, for example, you can use the Rayleigh-Jeans law as an approximation to the Planck spectrum, which is twice kT by lambda squared. If you look at the non-thermal emission, which is plotted also in this graph, it is due to synchrotron radiation. And synchrotron radiation arises due to relativistic electrons radiating in the magnetic field. And this synchrotron radiation is polarized, and its intensity increases towards lower frequencies, as can be seen in the graph here. Now, for example, if you have electrons with energies of the order of 10 million electron volts, remember that the rest mass of the electron is only half an MeV. So this is a very 10 MeV electron is an energetic electron. And if you have one Gauss field, it will have synchrotron radiation peaking around 1 gigahertz. These are the kind of radio emission that you see from non-thermal sources. So going back to Jupiter, what is happening with the Jupiter is that Jupiter has actually a dipolar field with equatorial field intensity of the order of the 4 Gauss crystal. It is mostly dipolar in nature, as is sketched in the figure here. Now, it is believed to be generated by internal dynamo, much like the magnetic field of the Earth, which is also generated by an internal dynamo. And if you look at what is shown in the bottom left picture, is the Jupiter in the center and the satellite Io going around the Jupiter. Now, the satellite Io is about 500 million kilometers from Jupiter, similar to the distance of the moon from the Earth. And the satellite Io is actually one of the most volcanically active body in the solar system. So it is spewing out tons of hot and ionized material every second and produces energetic electrons. So the magnetic field, which is provided by the Jupiter, and then there are these energetic electrons which are produced by the satellite. So you have energetic electrons in the magnetic field, and the synchrotron radiation results due to that. So the two bright spots that you saw in the image of towards when you were imaging Jupiter in radio correspond to the orbital position at Io. That's where the maximum amount of relativistic electrons seen, and that's where you see the synchrotron radiation. So this is, for example, this is one example of where. This is an example where the optical picture of Jupiter would have told you nothing about the field or the relativistic electrons, but the radio observations tell you about the magnetic field, about the relativistic electrons, and the radio emission from them. Okay, moving on. Atomic hydrogen is one of the most abundant elements in the universe. In fact, it constitutes 3/4 of the material amount of matter that we have in the universe. The question is, if you have atomic hydrogen, how do we detect this? Now, one of the most used spectral line in all of radio astronomy is the 21 centimeter line from the hydrogen. Now, this arises due to spin flip transitions in the ground state of the hydrogen atom. That is, the hydrogen atom in the ground state has a proton and an electron, and the protons and electrons spinning. Now, the spins can be either parallel to each other or they can be anti-parallel. There is a small difference in energy between the two levels, which, when the hydrogen atom splits between the higher energy state of parallel spins to lower energy state of anti-parallel spins, emits a frequency, a photon, which is which comes around 21.11 centimeters, or a frequency of 1420.405 megahertz. Now, this is a spectral line emission, and this can be, of course, detected by radio telescopes and has been done in the last 5 or 6 decades or so. Now, I'm just going to show one example of what the distribution of atomic hydrogen in external galaxies tells us, as opposed to the distribution of stars. Now, this is a picture of the Westerbork synthesis radio telescope in the Netherlands. It has 14 25-meter diameter dishes, and it is placed on a 2.7 kilometer east-west line. It works in the frequency range of 120 megahertz to about 8.3 gigahertz, and it has done pioneering work in the areas of pulsar, atomic hydrogen gas, radio galaxies. So what I'm showing here is on the left panel is the picture of Andromeda galaxy, which is also known as M31. This is the nearest spiral galaxy to the Milky Way. It's at a distance of about 2.5 million light years from us. And it's visible to the naked eye. You can see it as a fuzzy blob, about 3 degrees in size. That's what you see here. And its extent is about 100,000 light years, 100 kilo light years. The size of the Andromeda size extent is comparable to that of the Milky Way. Now, what you see on the left side, which is in the visible region of the spectrum, the light that you're seeing here is due to stars in the Andromeda galaxy, and also these stars ionize the gas surrounding them. So this hot ionized gas also emits thermal radiation, and that is what you see in the left side of the picture. What is shown on the right side is an image of the galaxy imaged by the Westerbork synthesis radio telescope in the 21 centimeter line of atomic hydrogen. Now, what is this telling us? Atomic hydrogen, since the 21 centimeter line of atomic hydrogen arises due to the presence of hydrogen atoms, this tells you the distribution of gas in the galaxy. The panel on the left tells you where the stars are, where the panel on the right side shows you where the gas is in the galaxy. Now, it is extremely important for us to know where is the atomic hydrogen gas and how is it distributed in the galaxy, because it is from this gas that stars are born. If you don't know where the gas is, then your information about the galaxy is incomplete. So this is the distribution of atomic hydrogen gas in the Andromeda galaxy. You can see that it is quite different in many ways. For example, there is a hole in the center of the Andromeda galaxy, whereas it's a very bright emission in the visible. The hole in the center of atomic hydrogen distribution implies that most of the hydrogen gas has been used up in producing the bright stars, and hence you see essentially pretty much an empty region. You also see, when people mute, can somebody is talking, can you mute it please? Can somebody mute?
Mr. Nagaraju, please mute.
Thank you. And what you also see in addition is the distribution of atomic hydrogen on the spiral arcs, which is not so clearly visible in the left panel of the figure. Now, another thing that one obtains from the studying the galaxies in 21 centimeter of atomic hydrogen is the kinematics of the galaxy. Because 21 centimeter line, since it's a spectral line, you can measure the observed frequency of the 21 centimeter line as opposed to the rest frequency, and that tells you about the rotation of the galaxy. And this has been done with hundreds and thousands of galaxies, and we know how the galaxies are rotating and the rotation curves and so on. You can also estimate the total gas mass of the galaxy, which is of course an important ingredient in understanding the star formation in the system. Now, what I'm showing in the next slide is actually about interacting galaxies. See, very often galaxies don't come in singles, but they come in groups of 3, 4, sometimes as big as groups of 10s and 20s. As you can imagine, the galaxies that are that close by to each other will be interacting with each other. This is what is known as tidal interactions, and tidal forces are similar to the ones that we experience whenever we go towards the seaside. You see the sea waves. Please mute the speaker.
Yeah.
Please mute the speaker.
Ms. Anandu Pradosh, please mute. Ms. Anandu Pradosh, please mute.
Malayalam speaker, please mute. Please mute.
Anandu Pradosh, please mute.
Thank you. So the tidal interaction that these galaxies experience between each other is very similar to the tidal forces that the sea experiences due to the moon and the sun. We see, for example, depending on the full moon and the new moon, the level of the sea changing, and the waves, you have high waves and low waves. Exactly the similar thing happens between the galaxies. But what is shown in the left panel is the optical image of the group of galaxies, which is a distance of about 10 million light years from us. And you see three little dots there, those are 3 galaxies, and that is telling you stellar light distribution. This is taken from the Columbus Sky Survey. But what you see on the right side is actually the image of this group made with the very large array radio telescope, and you can see there is a lot more gas seen all around in between the galaxies. And this is because because the tidal interaction between these 3 galaxies, the gas has been pulled out, and this is an extremely important information about the dynamics of the system. And we know, for example, how groups evolve, how galaxies evolve by looking at the dynamics of the system. And this can be seen only in the imaging of the 21 centimeter light, because it is the gas that is pulled out of the galaxies, and most often the stars are not pulled out. And this is, for example, the image of the VLI picture, very large array. It has got 25 meter diameter telescopes, and it has over a frequency range of 74 megahertz to 45 gigahertz, and it's a very versatile telescope. And the previous image that I showed you was made with a very large array. Now, moving on, we look at the nearest and very powerful radio galaxy called Cygnus A. Now, if you observe Cygnus A in optical, you see only a very fuzzy blob, like it is shown in the top panel. It is an elliptical galaxy. It's at a redshift of 0.05, or equivalently a distance of about 600 million light years. Now, but the elliptical galaxies quite often have what we call an active galactic nucleus in the center. Elliptical galaxies often have an active galactic nucleus in the center, and in fact, much of the optical emission that you see is due to the light from the gas that is ionized by the nucleus, actually. That's all that you will see in the optical, but however, what is shown below is a radio image of Cygnus A, and there is a little green square in this bottom picture, which is all that you will see in the optical, which is expanded here. That's what you see in the optical. But however, in the radio, you will see it's actually it's a very big radio galaxy. The extent of this is about 450,000 light years. It is as much as 4 to 5 times as big as the Milky Way. And in the center of this, which you call the core of the radio galaxy, there is a supermassive black hole in the center. It's got a mass of the order of 10 to the 9 times the mass of the sun. And the supermassive black hole produces jets of emission, which then bring in the energy from the black hole, they dump it here, and they produce this huge radio emission on both sides of the core. So once again, I would like to emphasize here, the color here represents intensity of radio emission, with the brightest radio emission being present in this place called hotspots. We have 2 hotspots here, and then there is diffuse radio emission flowing behind the hotspot. So there are 2 lobes and 2 hotspots and 2 jets that are coming out of the black hole. Now, just to give you a feeling for the luminosity from the source, second, compared to the luminosity from the sun, which is only about 10 to the 33 ergs per second. So it is some 10 to the 12 times as bright as the sun, and you will see it only in radio, not in optical. This is one example. There are millions of radio galaxies in the universe, and they have their own beautiful stories to tell us as to what's happening in the universe. Okay, so we're moving further away now. We're looking at the cosmic microwave background radiation. As some of you might know, this is a relic of the Big Bang. The Big Bang is an event that we believe occurred roughly 13.5 billion years back. And since then, the universe has been expanding. And to begin with, of course, it was very hot, temperatures of the order of maybe 10 to the 19 Kelvin or so. And as the universe is expanding, it is cooling. That is what is being shown in the left left picture here. When the matter was very hot, it was fully ionized and it was in equilibrium with the radiation. So, so the photons cannot escape from the region which is shown in yellow and orange. As the universe cools, temperatures of the order of 3000 kelvins or below, the matter starts recombining, the protons and electrons recombining and form neutral atoms. At that time, the photons no longer interact with the material and they fly directly to us, which is what we see today. This is very similar to what is shown in the cartoon on the right hand side here, where if it's a cloudy sky, what you see actually standing on the surface of the earth is only the lowest part of the cloud, which is the surface from which the light is last scattered. And you don't see beyond the cloud because light from there is not reaching your eye. That is the similar thing that's happening with the cosmic microwave background radiation. So, can we see this? How do we see this? And this is what I have discussed in the next slide. So, the surface of last scattering happens at a redshift of about 1,000 or so. Think of redshift as some kind of a scale factor or expansion factor for the universe. That means it was 1,000 times smaller compared to the present day universe. So the expected temperature of the cosmic microwave background radiation is about 1,000 times less than what it was when it left the last scattered surface, and it has been estimated that by the sky, starting with the 1950s, people have tried to make estimates of this background estimate. George Gamow, for example, estimated it to be 7 Kelvin.
Hello.
And however, 10 years later, Benziak and Wilson actually measured
ಸೆಂಟ್ರಲ್ಲಿ
it to be 3
ಪಾರ್ಟಿಸಿಪೆಂಟ್ಸ್
Kelvin.
ಅಂತ ಬರುತ್ತೆ ಸರ್.
We will discuss that in a moment.
ಅಲ್ಲಿ ನನ್ನ ಹೆಸರಿಗೆ ಹೋಗಿ ರೈಟ್ ಕ್ಲಿಕ್ ಮಾಡಿ ಕೋ ಹೋಸ್ಟ್ ಮಾಡಿ
For
ಸರ್.
example, the 1990s, we have
ಜಸ್ಟ್ ಪಾರ್ಟಿಸಿಪೆಂಟ್ಸ್ ಹೋಗಿ ಸರ್.
which has a infrared
ಹೋಗ್ಬಿಟ್ಟು
spectrometer on
ಎಸ್
it,
ವಿ ರಾಮನ್ ಅಂತ ಇರುತ್ತೆ
and
ಸರ್.
it has measured the black body temperature.
ಅಲ್ಲಿ ರೈಟ್ ಕ್ಲಿಕ್ ಕೊಡಿ ಸರ್. ಅಂದ್ರೆ ಐಪ್ಯಾಡ್ ಆಗಿದ್ರೆ ಲಾಂಗ್ ಪ್ರೆಸ್ ಮಾಡಿ ಕೋ ಹೋಸ್ಟ್ ಅಂತ ನನಗೆ ಮಾಡಿ ಸರ್.
What I've shown in the left hand part of the slide is that
ಮಾಡಿದ್ರೆ ಸರ್.
as the universe expands, for example, if you look at so hot that most of the radiation would have been peaking around gamma rays.
ಎಸ್ ವಿ ರಾಮನ್ ಅಂತ ಇರುತ್ತೆ.
As the universe cools, and if you come to present day,
ಬರ್ತಾ ಇಲ್ವಾ
the temperature
ಸರ್? ಮ್ಯೂಟಲ್ ಮಾಡಿ. ಮ್ಯೂಟಲ್ ಮಾಡಿಬಿಟ್ಟು ಆ ಗೆಸ್ಟ್ಗೂ
and one of the interesting
ಇದು
aspects
ಮಾಡಬೇಕು.
of the black body radiation is as the temperature decreases, it will still remain a black body, but a black body of a different temperature. That is exactly what
Sir,
is
you are the
seen by
co-host.
Benziak Wilson.
I guess you can do, sir.
Here is a brief background to what Benziak
ಅಂದ್ರೆ ಎಸ್ ವಿ ರಾಮನ್ ಅಂತ ಆಯ್ಕೆ ನೋಡಿದಾಗ ರೈಟ್ ಕಾರ್ನರ್ ಅಲ್ಲಿ
you can see that behind the
ರೈಟ್ ಕಾರ್ನರ್ ಅಲ್ಲಿ 3 ಲೈನ್ಸ್ ಬರುತ್ತೆ ಸರ್.
that is what they use.
3 ಡಾಟ್ಸ್ ಬರುತ್ತೆ, ಒಂದು ಸ್ಟ್ರೈಟ್ ಲೈನ್ ತರ. ಅದು ಕ್ಲಿಕ್ ಮಾಡಬೇಕು.
It is a 6-meter horn antenna, and that was
ಅದರಲ್ಲಿ 3 ಲೈನ್ಸ್ ಅನ್ನೋದು ಡಾಟ್ಸ್ ತರ ಬರುತ್ತೆ. ಸ್ಲೀಪಿಂಗ್ ಲೈನು.
They made an image of the whole sky using this antenna, and they found that
ಕೋಹೋಸ್ಟ್ ಮಾಡಬಹುದು ಸರ್. ಕೋಹೋಸ್ಟ್ ನೀವು ಇನ್ನೊಬ್ಬರು ಕೋಹೋಸ್ಟ್ ಮಾಡಬಹುದು.
emission that you see, the color that indicates here the temperature of the CMBR emission.
ಅಂದ್ರೆ ಐಪ್ಯಾಡ್ ಅಲ್ಲಿ
3.5 Kelvin, and it is isotropic. That means you see it in all directions. It is unpolarized, which means it is of thermal origin.
ಅಂದ್ರಲ್ಲಿ ದ್ವಾರಕಾ ಸರ್ ಮಾಡಬೇಕಾಗಿದ್ರೆ ಹೋಸ್ಟ್ ಮಾಡಬೇಕಾಗಿದ್ರೆ
What has been done since the measurement of Celsius and Wilson is that
ಇಲ್ಲಿ ಬಿ ಪ್ರಕಾಶ್ ಮತ್ತೆ ಬಿ ಪ್ರಕಾಶ್ ಕೇಳಬೇಕು ಸರ್, ಅದು ಮ್ಯೂಟ್ ಮಾಡಿ ಅಂತ. ಒಪ್ಪೋ A112
you
Yes,
want
sir.
to
Yes, sir.
really
You mute ಮಾಡಿ ಸರ್. ಹಾಂ,
observe
yes, sir.
at higher frequencies like
ಅದು ಸರ್.
150 gigahertz, you have to fly
Sure,
satellite.
sir.
And this was flown in 1990 by
ಆಯಿತು.
NASA Cosmic Background Explorer, which had a far infrared radio
Yes, yes,
amplitude
yes, yes.
spectrometer, which is
ಮ್ಯೂಟ್
called
ಆಯಿತು ಸರ್. ಈಗ
FIRES.
ಚೆನ್ನಾಗಿದೆ. ರೈಟ್
And
ಸರ್.
it could measure the
ರೈಟ್ ಸರ್. ಥ್ಯಾಂಕ್ ಯು ಸರ್.
intensity of the sky emission in the frequency range of 60 gigahertz to
ಶ್ಯೂರ್ ಸರ್. ಶ್ಯೂರ್ ಸರ್.
3 terahertz.
ಆಲ್ಮೋಸ್ಟ್.
So what is plotted here, in fact, those dots with error bars on them, is actually measurement. Now, these measurements were so accurate that they could not even show the error bars. If they plotted normally 3 sigma or 5 sigma error bars, you would not even see them. So the error bars that are plotted here are 400 sigma. So that tells you how accurate these measurements are. So all these data points that are shown here is the measurement from FIRES Kobe measurement. Now, what is drawn here, this solid line, is actually the Planck spectrum for a 2.725 Kelvin black body. I would like to emphasize that it is not a fit to the data points, but it is actually the black body's Planckian spectrum. You can see that the fit is excellent. So this is probably the best measurement we have ever made in all of astronomy. And this is telling you very clearly that there is this relic from the Big Bang that you can measure all over the sky. And FIRES or Kobe also made an image of the entire sky in at these frequencies, which is what is shown on the right-hand panel. And the blue and green colors here indicate variation in the intensity of the radio emission, and it is believed that either it tells you something about the temperature fluctuation in the early universe that are responsible for the structures that we see today. So I would like to emphasize once again that this is something, CMBR is something, for example, that the only way you can detect it and measure it is through radio observations. Now, having said all these examples, I would like to also briefly mention two of the telescopes that have worked and working in the country. One of them is the Ooty Radio Telescope. It is a 30 by 500 meter parabolic dish, works at a frequency of 327 megahertz, and it has done pioneering work in the area of quasars, interplanetary scintillation, and radio recombination lines. The next slide I'm showing is the Bengaluru Radio Telescope. It's an array of dipoles. There are about 1,000 dipoles which are spread over half a kilometer by 1.5 kilometers extent. It works in the frequency range of 30 to 160 megahertz, and it has carried out outsky surveys, observed pulsars, solar radio emission, and radio recombination lines. The next slide shows you about the giant meter wave radio telescope, which has been in operation for almost 20 years now. It has got 30 45 meter diameter dishes. You can see about 4 or 5 of them in this picture. It works in the frequency range of 150 to 1420 megahertz. It's near Pune, and it gives you a maximum separation between the antennas of the order of 25 kilometers. Now, there is another telescope in which some of us worked. This is the Murchison Wide Field Array, which is in Australia. It has got 128 tiles, each of 16 dipoles. It works in the frequency range 80 to 30 megahertz, and it has carried out surveys of the sky. It has observed radio galaxies, quasars, and epoch of reionization. So I think this is just a close-up of one of the dipoles that we have used in Murchison Wide Field Array. And incidentally, Raman Research Institute built all the receivers that were used in this telescope to observe the sky at these frequencies. So I think with that, I would like to stop and ask any questions if there are. Thank you very much.
Professor Dwarakanath. Now the floor is open for any questions or comments. Those who want to ask questions, you may raise your hand and then ask. I have a rather simple question. You said the UT radio telescope operates at one particular frequency. Gauri Bindur at one particular frequency. How these particular frequencies are selected or how they are really made to work only at one particular frequency?
Correct. So, okay. For example, the UT radio telescope, which is working at 327 megahertz, the frequency was chosen for the following reason. I mentioned in my talk that the hydrogen atom has a spin flip transition at 1420 megahertz. That's a spectral line. Similarly, if you ask what is the spin flip transition in the ground state of the deuterium atom, that will come at 327 megahertz. Now, deuterium is abundance of deuterium, that is, how much deuterium is present in the galaxy, is an extremely important input to how the universe has evolved over time. Because deuterium is synthesized in the early universe, so if you want to know how much deuterium is present and what happened in the early universe, then you need to work at 327 megahertz to observe the deuterium spectral lines. That is how that frequency was selected. Now, Gauri Bindur, which works at a low frequency of 30 megahertz, that frequency was chosen largely to image the emission from the Milky Way, which, because it is non-thermal emission, has very bright intensity and lower frequencies. So that is how we choose 35 megahertz for Gauri Bindur radio telescope.
The song you want to ask questions?
I can't hear you, sorry.
Oh, speak up loudly. I'm not hearing you. Unmute. Okay, now you can speak. Professor Swami, you can ask now. When you speak, don't move your head. Speak only in one position. Then it will be better transmission.
Sorry, is the question how to distinguish between thermal and non-thermal emission?
Yes.
Okay. Yeah, that's a fairly straightforward one to do that. As I showed in one of the, maybe I can show the slide. I'll show the slide. See as you can see in this, are you able to see the slide?
Yes.
Okay. So what you can see in the plot is, y-axis is the intensity of the radiation, x-axis is the frequency increasing to the right side.
Yes.
If it is non-thermal emission, the non-thermal emission increases in intensity as you come to lower frequencies. Whereas if you have thermal emission, it increases towards increasing frequency. They have exactly opposite trends, as you can see here. One is non-thermal emission is increasing in intensity towards lower frequencies, whereas thermal emission is decreasing as you come to lower frequencies. That is one way of distinguishing between the two. The second thing is thermal emission, which is like a black body emission, is unpolarized, whereas non-thermal emission is polarized. That's another way of distinguishing them. here. Maybe you can type in the question. Is there a way to type in the question?
Yeah, they can type it. In the meantime, I have a question.
Yeah.
What about the best resolving powers of the radio telescope? How best we can resolve the various objects in the sky? I mean, can you talk
Yes.
about that?
See, there is a range of there is a whole range of telescopes where the resolution varies enormously. For example, if you take a telescope like the GMRC, you can get resolutions of the order of, let's say, few arc seconds. Let's say 3-4 arc seconds resolution. Now, we also use techniques called VLBA, that is very long baseline array, where we have telescopes which are spread across continents. For example, you can have one in the east coast of the US, another one in the west coast, a third one in Chile, a fourth one in Antarctica. It's possible to combine the signals from all these telescopes and produce resolutions of milli-arc seconds to micro-arc seconds. So there's a range of resolutions that we can achieve depending on what kind of telescopes that we use.
Sir, I have two or three questions, Professor Kagli.
Yeah, please ask. Okay, go ahead.
Dr. Dwarakanath, thank you for a nice picture.
Thank you.
My first question is very, very elementary. Can you please tell me, in treating me as even a middle school student, why is this temperature this BB radiation temperature comes down to 2.7 K?
Yes. Okay. The reason is the following. Imagine that there's some echo coming. Some echo is coming.
Yeah, your voice problem is
Can I go ahead?
Yeah, please go ahead.
Yeah. Okay, so imagine what's happening is, suppose you have a box of hot, ordinary matter in it, and suppose you expand the box, keep on expanding the bags, then because of the adiabatic losses, the gas inside will cool. So that cools as the volume, the density, matter density decreases as the volume of the box. Now, if you now have a box of relativistic fluid, which is basically the photons, then when you expand the boxes, expand the box, it will decrease as radius to the power 4. That is, if you look at, imagine that the box is a spherical box and it has a radius r, it decreases as r to the power 4. So what is happening is, to begin with, imagine that very close to the Big Bang, the matter was very high density and in a very small volume, and with time that box has expanded. So the radiation density inside the volume keeps on decreasing with time, and given the amount of time that it has taken, that is about 13.5 billion years, the gas which was hot of the order of 3000 Kelvin now has cooled down to about 3 Kelvin. That is why the gas is cool, because it was contained in a small box, now it is much bigger. That is the understanding that we have.
Okay, sir. My doubt concerns regarding, see, every photon in the beginning had the same energy. Photons have the same energy. The space has been made enlarged, as I understand. In that situation, how is that the temperature of photon or the energy of photon decreases? Is it over what you are considering?
Yeah, that is because they have undergone a cosmological redshift.
I see.
That is why the energy has come down. They have undergone a cosmological redshift.
Thank you, sir. Yeah, I got it. My next two questions are, one is,
Okay, go ahead. Please ask. We have time. No worries. Please ask.
do we have polarimetric studies in India now? Are our, detectors, antenna? Yeah.
Yeah. For example, if you look at the GMRT, it can measure both the polarizations. It can measure both the right and the left polarization, so that you will get a full picture of radio emission. Yes.
Yes. So my last question is, with the latest technology, I feel like our antennas are still in the same traditional structure. Hasn't the latest technology helped in, a kind of new kind of technology for radio observation?
It has helped in the following sense. See, when you look at the picture of GMRT that I showed, it has got all these dishes and so on. That is, uh, there is no big change in that itself. But once you collect the signals, how we process the signals, that has undergone a sea of change in the last 20 years or so. We can do tremendous number of things now which we were unable to do 20 years back. So all the modern technology has gone into what we call as receivers and the electronics. That's where the big maximum change has happened.
Thank you, sir. Thank you very much.
Sir, excuse me, sir. Can you hear me now?
Yeah.
Sir, I have one question. GMRT telescope antenna is in disc shape, but Gauri Biznur shape is different.
Correct.
Just I want to know why shapes are different.
Yeah. Right. See, in Gauri Biznur, what we have done is we have used simple dipoles. You take a piece of wire. Suppose you want to observe at a wavelength of, let's say, 30 meters. So basically, you take a wire of length which is half the wavelength, which is lambda by 2, cut it in the middle, and then make a little separation. You can take the current out of those dipoles, and you can make an antenna. Low frequencies it is possible. Now, GMRT works all the way up to 1400 megahertz. Now, what we are doing there is that the dipoles or the horn that is collecting the 1420 megahertz radiation is situated in the prime focus of the dish, and the GMRT dish itself is about 45 meters in diameter. This is to make sure that we collect enough radiation, because astronomical signals are very weak. So this 45-meter diameter dish collects the radiation, and it focuses all the radiation towards the horn that is present in the prime focus. So it is a different design. So we are not simply using just dipoles there, but you're using the dish to focus the radiation onto the dipole and then collecting the currents and signals from the dipole.
Thank you, sir. Thank you very much.
Mukul Sajiv, you might ask your question. Mukul Sajiv.
Sir, am I audible?
Yeah,
Yes.
you can ask.
Sir, in case of the Cygnus galaxy, what is the reason for that two lobe-shaped structure image instead of a uniform image? And also, what is the reason for that two hotspots?
Correct. Okay. So here is the image. Can you see the image?
Yes, we can.
Mr. Gokul, can you see the image?
Yes, sir, I can.
Okay. So the thing is, this is a radio galaxy. The Cygnus here is a radio galaxy. It has got a black hole, supermassive black hole at the center, which are marked as core here. So the black hole puts out two jets of radio emission. In fact, you can see one of the jets very clearly here. The one here which is called jet. There is something else called counter jet here, but you see here the jet. So the jet that is the one which is carrying all the particles in the fields. The jet has a certain pressure. When this pressure equals the pressure in the intergalactic medium, which is outside of the galaxy, then the jet deposits all its energy at that point. That is the place where the hot spot is. And from there is something called a backflow, where most of the electrons and fields have actually flown back. So, usually the black hole is surrounded by an accretion disk with two openings, which are perpendicular to the accretion disk. The two jets that you see here are coming from the two openings, and that is where you see two jets and 2 lobes and 2 hot spots. Does that answer your question?
Okay, sir. Thank you.
Gokul? Okay.
No further questions. I request Dr. Swami to propose a formal vote of thanks.
Thank you. Thank you very much, sir.
Sir, I have a question.
Okay,
Thank
Dr.
you.
K.S. Dwarakanath, the former eminent professor and scientist of Raman Research Institute, Bangalore, has delivered an excellent and very informative talk on the radio universe. All of us have enjoyed your talk very much, sir. On behalf of Karnataka Physics Association, Bangalore, I express my profound thanks to you, sir, for sparing your valuable time, sharing with us your view on the radio universe. Thank you very much, sir.
Thank you.
I express my profound thanks to Dr. Raghavendra, Coordinator, Janadhara, for providing Zoom facility to have a online talk. Thank you, Dr. Raghavendra. I am thankful to all the members who have actively participated in this important online talk. I am thankful to President of Karnataka Physics Association, Professor Basavaraj Kagli, for arranging this important talk. Thanks to one and all. Thanks, sir. Thanks to all of you.
Thank you.
Thank you, Professor Dwarakanath, for a very informative talk. So now
Thank
we
you.
close the meeting. Now we close the meeting. So we'll
Excuse me, sir.
come back maybe next week.
Excuse me, sir.
Somebody is saying, excuse me.
Yes, sir. This is Ishwar, a 12th standard student. So
Okay.
I would like to have an elementary doubt about this session.
Yeah.
So, since the propagation of radio waves are affected by intergalactic medium's density
Yes.
and its composition, how radio telescopes are precise with the imaging and these radio galaxies? How are they such precise in capturing such images of these galaxies, which are far apart?
You see, yes, they are traveling through the intergalactic medium, but that doesn't stop us from detecting them and imaging them. No? What is the concern you have?
Since the intergalactic medium is denser and high in composition, it shows dispersion and scattering, which just hinders the imaging of the telescopes, right, sir? So how do we get precise images of those galaxies?
Okay. For one thing, intergalactic medium is not dense. It's extremely rarefied, and it doesn't. There is very little dispersion happening in the intergalactic medium, so it doesn't really bother the signal so much. The signals can still be detected and we can image them. There is no serious issue. The second thing is, if you work at reasonably high frequencies like 1400 megahertz or 2000 or 5000 megahertz, the effect of the medium is even less compared to lower frequencies. So it's almost, they just pass through the intergalactic medium without any problem.
Okay, sir.
There's no problem. There's no problem with that.
Okay, sir, that's it.
Okay.
Sir, may I ask a question, please?
Yeah, sure.
Sir, you have shown the image of Andromeda galaxy in the radio waves, right?
Yes.
I have a doubt. We have already taken the supermassive black hole image of our galaxy.
Yes.
But we know there may be plenty of disturbances within the dust cloud. So how we have taken the image of the supermassive black hole?
See the basic technique that is used to image the supermassive black hole in our galaxy is the same as that we do for imaging any other source. The reason why it has been possible in the last few years is because we're able to achieve the kind of resolution that is required to image the black hole in the Milky Way. Because as you can imagine, if you want to image the black hole or the region surrounding the black hole, you need very high resolutions. And that was not possible until recently. So that has been possible now, and that's what I mentioned. You can have telescopes now across the continents, starting with Chile to the United States to the North Pole and so on. So we're able to connect signals from these various telescopes, and that is how we're able to make the image of the black hole now.
Thank you, sir. Thank you.